Hello, everyone, again. Thank you for joining us with Pyramids Chapter. I'm Furat Musa, the Chapter Technology Transfer Committee Chair for Pyramids Chapter. Of course, I'd like to welcome Dr. Omar Abdelaziz first and thank him for giving us this opportunity to learn from his valuable experience. And also, I would like to welcome all the co-hosting chapters, Alexandria, Falcon, Jordan, Lebanese, and Saudi Arabia. They're all co-hosting chapters with us today. Dr. Omar, if you would allow me before we start, I would like to talk briefly about what ASHRAE does for whoever doesn't know. Just a very brief introduction. ASHRAE stands for the American Society of Heating, Refrigerating, and Air Conditioning Engineers. It's an American professional association seeking to advance HVAC and refrigeration systems design and construction. It has over than 50,000 members in more than 130 countries worldwide, from different fields as building service engineers, architects, mechanical contractors, building owners, manufacturers, and others that are concerned with the HVAC and refrigerants industry. ASHRAE also is a non-profitable organization in which most of the people who are working on it are volunteers. It's well known for publishing HVAC technical standards, as most people know, but it also funds research projects, offers continuing education programs, and aims to improve building services engineering, energy efficiency, indoor air quality, and sustainable development. And the past few years, sustainability has been the theme for every ASHRAE president. And I will share with you in the chat box the links for the ASHRAE website for whoever wants to learn more about it. And also we have the ASHRAE Awards and ASHRAE certificates that you might want to learn about it as well, because they are very beneficial. I will share their links as well, and the membership link as well for if you want to know about the benefits of the membership. And please like and follow our page on Facebook to be updated with our coming programs and events.
Before I start, I would like to thank the hosting chapters for inviting me to speak on this interesting topic of the next generation data center cooling technologies. This is a very timely topic. I also would like to thank all the audience who are here today, coming from different parts of the world. I see many Arabic speaking people, but I also see many non-Arabic native speakers. So I will give my talk today in English. However, if you would like, you can enable caption in Arabic. So at the bottom of the screen where you have the Zoom, you can click on more, and then you click on captions, and then you can select the language that you want your caption in, and it will easily translate what I say in the language that you prefer. All right. Now I probably can start. So my name is Omar Abdelaziz. I am an associate professor of mechanical engineering at the American University in Cairo, and I am the student activity chair at Pyramids Chapter, and I do other activities as well internationally. Today we will cover data center cooling. First, we would like to know why we need to cover this. So looking at the growth and the energy demand, what are the key performance indicators? And then what are the conventional cooling technologies? This is important just to build the basis, right? Everyone hopefully know what is the conventional air-based cooling technologies in data center. And then we move forward and talk about the advanced cooling technologies like direct-to-chip and immersion cooling technologies and other emerging technologies in conclusion. So the IEA has published a very interesting report called Data Center and AI, or Energy and AI, and it predicted the global installed data center capacity in gigawatts. And it's the number is alarming. As you can see here, you see there was very little growth between 2005 and 2016. The growth was not that big, right? But since 2016, something happened, which is the advent of AI. And with the advent of AI, the growth has been almost exponential. And you see this at the enterprise level, at the co-location level, and the hyperscale level. But the high increase is in the co-location and in the hyperscale data centers. The difference between enterprise, co-location, and hyperscale is that enterprise data centers are data centers made primarily for companies or for telecom companies and things like that. So it is more controlled data centers. And you can see that the growth is not that big, although recently we have seen a little bit of growth because again, AI is increasing the demand for IT in companies. Co-location are data centers that companies built not for their own use, but to rent out data center spaces within their data center. So, for example, I am a new company in the IT space, and I want to put uh, 10 racks, right? Where do I put the 10 racks? Do I just put them in my attic? Probably they will burn out. So I go to this co-location data center and I rent a space to put my racks. So these are co-location, and again, the demand for co-location data center is growing, especially in countries where there is a lot of growth um, in IT companies, especially small and medium enterprises. Hyperscale is like the big name companies that work in IT that either use it for their own use or for cloud computing. Now, if we look at the energy used, so this is the gigawatt. If you look now how much energy these are used, you will see that the growth, it went from 150 terawatt hours in 2005 to now almost 500 terawatt hours in 2025. This is 3x increase in just 20 years. That's a significant increase. And again, we see the same trend, almost no much increase in the first 10 years. However, there is a significant growth in the last 10 years. Now, what I like about the curve in the bottom here is how much cooling is consuming, right? Look here, cooling in the past was a significant chunk of the equation, right? So the green is cooling, the server is the light blue. So basically, cooling was almost as much as the light blue, right? That means that you have to spend a lot of energy to cool your data center compared to just running your data center. Now, look, with the advent of all of the cooling technologies that are available, and we will discuss some of these today, you will see that the cooling component, it's roughly the same. The green piece, it doesn't grow much, but you see that the light blue piece grew a lot, right? That means what? That means that for the same amount of IT, we are using much less cooling. And we will see another chart that directly shows that. Also, it's important to note here that US, China, and Europe contribute to about 85% of the global demand in data centers. So why cooling matters? Because IT equipment like servers and networking gear, they produce significant amount of heat. And I'm not sure if any of you have been near any of these or have been into any of the data centers. You will hear the fans whizzing, and the hot aisle can get pretty hot. However, air cooling becomes very ineffective when rack density exceeds 30 kilowatt. There are some technologies to get us around 50 kilowatt, but that's about it. Cooling systems can account to 30 to 50% of the facility energy use. So when we use air-cooled designs, the power use effectiveness is very low. And the efficient cooling can significantly reduce the cost and increase the reliability, because one of the major things that impact the reliability of our IT equipment is how hot they get. And if for any reason air does not get into our data center, they get too hot and the rack would shut down. So now with high density AI equipment, as you can see with some of the recent chip manufacturers, right? How can you cool these with simple air-cooled equipment? You will not be able to do that. So there needs to be new technologies. Before we proceed, we need to understand what are the performance metrics that we have to use in order to easily compare and benchmark between different data centers. Also, these help us to track the performance of year over year and also try to find how we can improve our performance. The one and foremost used performance metric is called the power use effectiveness or power usage effectiveness, PUE for short. And then there is water usage effectiveness, WUE. PUE and WUE are kind of the most used KPIs in data centers. And then there are some recent KPIs that are defined recently, like the CUE or carbon usage effectiveness. This is with the new impact of sustainability, the DCIE or data center infrastructure efficiency, energy reuse effectiveness, and cooling efficiency ratio. Maybe I need to increase this a little bit just to show what's happening here. If you have a data center, this is the IT load, 66%, cooling 27%. There are some electrical equipment, other 1%, lighting 1%. These together would make the power usage effectiveness 1.5. So the power usage effectiveness is just by the total energy used divided by the IT usage. Ideally, you want this to be 1.0, but is it possible? Probably not, because you still need a little bit of lighting, a little bit of electrical equipment, because you have UPS and such, and you need to cool the equipment, right? People know that 1.5 is typical. However, we are now going down to 1.2 and even lower, and it can be influenced significantly by the ambient conditions. So if you are operating a data center in Abu Dhabi, it's gonna be much higher PUE than operating a data center in Copenhagen or in a place that has very low ambient conditions. So in 2023, this organization here did a survey of 558 data centers, and they grouped them by the capacity. So small data centers all the way to hyperscale data centers. And they found out that the average PUE ranged from 1.69 for small data centers to 1.44 to large data centers. But even the 1.44, this is the stock average. This is not the new technology. Because now the new technology is about 1.2. If you go into one of the major companies like Google and you look at the data center tracking website, you will find that they are claiming less than 1.1 already. And this is a significant improvement in energy efficiency. The other thing is water usage effectiveness, which is how much water we are using over the year divided by how much the IT used in kilowatt hour. And basically it indicates the water used for cooling cooling water, cooling towers and things like that, humidification and so on and so forth. And we want the WUE to be as low as possible. However, in dry areas, you need to humidify. In some areas, you use water for direct evaporative cooling, and that would increase WUE but reduce the PUE, right? The WUE is especially important when you are in an arid area, because in an arid area, you don't want to use water. A study was done by Lawrence Berkeley National Lab in 2016. They found out that the average WUE in the US was 1.8 liters per kilowatt hour. And they estimate that if you have a 100 megawatt data center, what that would mean is that you will end up with consuming 1.1 million gallons daily. That's a significant amount of water. However, if you look at how much water is needed at the power plant, and that was the crux of this figure here, right? Looking at the difference between how much water you consume on site versus how much water you consume at the power plant. And you can see that the consumption on site is much, much smaller than the consumption at the power plant. And people usually forget about this interesting point because they care about just reducing water on site. Maybe that would increase PUE, but if you increase PUE, you are going to increase the water that is consumed at the power plant. So the other metrics for COE, for example, it's basically the CO2 emissions ratio divided by the IT energy consumption. The DCI is the reciprocal of the PUE. It's the IT energy over the total facility energy. ERE is very important, especially in areas where you can use the waste heat from the data center in the buildings around you or other industrial process heating using high temperature heat pumps or so on. So with ERE, this is a new concept. I'm not going to talk too much about it in today's lecture, but the idea here is to use the waste heat from the data center and try to up that heat to usable temperature that can be used to heat the dwellings, heat pools, provide the preheating for boilers and so on. And then there is the CER, which is the measure of cooling system effectiveness. Again, another interesting concept or metric that tells us what is the quality of the cooling system. Do you have a good cooling system or a poor cooling system? All right. So data center. So just to understand what is the anatomy, how does a data center look like? If you have an enterprise data center or if you have a co-location data center. Typically, a hyperscale data center would look similar to an enterprise data center. Maybe some of the architecture would be a little bit different. Like the difference between an enterprise and hyperscale is the distribution of the data hall. In a hyperscale, they will try to make the data hall symmetric, and they push the electric room on the periphery somehow. So it's kind of a similar in sorts, but in this enterprise design, what they do is they put all the air handlers on the perimeter. They have the data hall in the middle here, and all the electrical equipment with the batteries in the middle, right? There is the 12 kilovolt room here. So this is the switch gear. You have storage rack for testing, right? And here you have the point of presence and point of entry for all the people who operate your equipment. And this is the admin building. Of course, you have a mechanical yard where you have your chiller that basically supplies all the chilled water for your air handling equipment. If we look at the co-location, now co-location is a little bit different. It's a different animal. And the reason why co-location is different is because it operates as you are trying to always expand. You are renting out the space. So here you have computer room A, and you can see they are renting out this space or renting out this space or renting out this space. So you can rent out one block at a time. And typically, they are designed such that the raised floor can be reconfigured for anyone's or any renter's rack placement configuration. And here you can see that the computer room air handling units are placed in the middle and they usually provide some spare units to like just in case in the future they need to increase the capacity. Also, they have to always design for extension or expansion in the future. All right, this figure is very important for any data center design engineer, because you need to know like how cool or how much you want to cool your building. Do you want to provide it at 25 and 50%? What is the comfort conditions, right? It's not comfort conditions, it's more of appropriate performance conditions. And you can see that you can operate according to ASHRAE TC 9.9, which is the Data Center Cooling Technical Committee, and ASHRAE 90.4, which is the standard for data center. You have the recommended zone, A1 zone, A2 zone, A3 zone, and A4 zone. So the difference between recommended and A4 depend on many things, mostly related to the reliability of the equipment and the supplier, right? The rack supplier. What does the rack supplier means? But you can see that you would operate in A1, like very comfortably, A1 here, between 15 degrees C and 32 degrees C. So you don't need to keep the data center at 25. You can keep the data center at 30 or 31 or 32 without compromising the performance. Of course, everyone tries to design here, 20 or somewhere here. Why? Because this is safe performance. But no, you don't need that. You can operate all the way at here, right? So if you design here, you are actually still within the safe region because you are still below the A2, well below the A3, well below the A4. And if you design with proper factor of safety, you will always maintain your performance in the A1 window. The conventional design is simple. We have data centers, these, racks. I tried to design them with AI, but it was poor design. So we have racks here. You have raised floor. You have the cold air blown from the raised floor entering the data centers. And from the back, what is happening is the hot air leaves and goes into the CRA. The CRA pushes the cold air down in the distribution in the underfloor cooling and so on. So the key components here is that you have a crack or a CRA, these white boxes in the back, right? And if you have a CRA, a computer room air handling unit, then you need a chilled water loop with a chiller. If you have a CRAC, computer room air conditioning, then you have a DX system that provides the refrigerant at the right conditions. These systems have been widely deployed. People know how to use them, how to design them, and I don't need to dwell on them too much. What is new here is the direct evaporative cooling. Can we use direct evaporative cooling? And I attended a course, an ASHRAE course, I think it was maybe almost a year ago, and I was surprised that Fortune 500 companies operate or rely exclusively on direct evaporative cooling in Arizona, very hot climate, Georgia, very humid climate, Alabama, very humid climate, Nevada, very arid climate. So arid and hot climate, Arizona and Nevada. Again, humid climate, Georgia and Alabama. So you can design your data center to be cooled using direct evaporative cooling and perform really well. So you can see here, this is the black here is the recommended zone, right? And the plots here in this chart is just for the Phoenix Ski Harbor International Airport weather. So basically, the hours of the year where the point is plotted on the psychrometric chart. So where is the worst case condition here? The worst case is where you have the hottest temperature, right? And this is the worst case, right? this is kind of the worst, or maybe this is the worst case. Probably this is the worst case, right? Because this would have the highest ambient condition, highest wet bulb temperature, right? So if you do direct evaporative cooling, you go all the way here, right? And then you allow the room to cool down to, again, because these are in IP, not SI, but when we say 31, so 85, so you can easily go from here to 81 and allow the room to cool again. So there is no problem because it's a sensible heating, or the load is sensible heat factor of 1. So if you supply the room with conditions here, right? Typically, they stay at 80%. So you supply it at these conditions, right? Then you have a lot of airflow rate. You push a lot of airflow rate, but you still would stay within the A1 region. Any questions here? Please feel free to ask questions if you have. I'll look quickly here in the QA box if there are any questions. So the source of the chart, well, this is the IEA, the source of this chart. Sorry. The source of this chart is IEA, the International Energy Agency, and the link is provided in at the end of the references. The comparison between crack and CRA in terms of electricity consumption and lead. Crack usually, so I forgot to put this chart, but usually crack would have much higher energy consumption compared to CRA, but crack is used with smaller systems. So if you don't have a big data center, you cannot justify the use of cooling of a computer room air handling unit. You probably it's sufficient to use a computer room air conditioning. So that's why in this chart here, when you have small capacity, the PUE is high because typically these rely on crack and not crack. Zohaib is asking about how wet bulb, dry bulb, relative humidity, and dew aligned, and how select range of temperature and humidity set points. I'm not sure I know which slide you are asking. Can you say which slide is this? Are you talking about this slide, Zohaib? All right. So until Zohaib clarifies the question, I will see later. In WE, 1 million gallon per day is used to cool down 100 megawatt. Is that a problem? If that is recycled, that should not be a problem. But if it's not recycled, it cannot be recycled because the water is typically evaporated into the air. So you cannot recycle that, and that's the problem. How does the humidity affect IT equipment? This is a very important question. So one of the companies that worked with this, they found out that if the supply temperature, supply humidity is less than 65%, 98% of the time, there is no problem whatsoever. But if it's more than 65%, 2% of the time, it can be a problem. So basically what they do is and that is add the inlet to the equipment, right? So you have to, we typically, if you see here, right, there is a mixing happening. So you provide it at 80% and then you mix, so it becomes 65%. So usually, as long as it's 65%, right, you operate at 65%, there is no problem. And the limit or the demarcation is 2% of the time higher than 65, you can be in trouble. But 2%, if you are 98% of the time or more below 65, you are okay. All right, moving on. So this is a very important slide because here people typically use the design ambient conditions based on this wet bulb and the mean coincident dry bulb. But when we use data centers, we cannot rely on these conditions because these conditions are for a typical year. Data centers, we typically use the either 10-year worst extreme conditions, 20-year extreme condition, or the 50-year extreme condition. Typically, if I am designing a center that is gonna stay and work forever, I would design it with 50 years extreme conditions. So in Cairo, Egypt, it would be 47 dry bulb and 28.8 wet bulb temperature. All right, one of the new innovation is the pumped refrigerant economizer, because with pumped refrigerant economizer, you can significantly reduce the PUE. Here you can see what you do is you have a compressor and you have a pump and typically a condenser, and you have your evaporator in your crack, right? So in this crack, you add um, a pump that at the time when the ambient conditions is cold enough to not need the compressor, you actually pump the refrigerant or create a pump loop. And by creating the pump loop, you reduce the power. As you can see here, if you are in a pump loop, the compressor consumes 0.6 kilowatt. If you are in a compressor loop, the compressor consumes 8.5 kilowatts. So the difference between a pump loop and a non-pump loop is significant, 0.6 versus 8.5. And you can see here that with a full compressor, the PUE is 1.28, with a partial economizer phase is 1.17, and with a full economizer phase, this is gonna be even lower than that, probably 1.1. Another new innovation is the passive rear door cooling. And here what we do is we place a heat exchanger, just a cooling coil at the back end of the rack. And by doing so, the hot air leaving the rack gets tempered or cooled before it leaves. So your hot aisle is not hot aisle anymore, and you can pack your racks more closer. And this is helping making the data centers more dense. Of course, here it relies on the service of the fan, so you do not need an additional fan here. It can use the chilled water or even the condenser water, because the air leaving the rack can be at 45 degrees or it can be at 50 degrees or more. So if you put here air coming from the condenser water at 30 degrees, you can temper enough. The good thing here is it provides a good redundancy, because if the CRA is out of service, this can provide significant cooling. And now it can provide up to 20 kilowatt additional per rack. So if the rack can provide 30 and this is 20 kilowatt, then you can go up to 50 kilowatt per rack. There is some challenges because of the dew point control, because you don't want to have any condensate on this coil. And also now you need to create a rack sealing, because you don't want this hot air to be spilled outside. So you want this door to be sealed well on the door. There is also the active rear door cooling. So it's similar to the one we talked about. However, here we use fans on the heat exchanger. And by using fans on the heat exchanger, these are hot swappable fan. And by using these fans, you can improve the heat exchanger significantly. Again, we can use either the chilled water or the condenser water, or even a refrigerant for cooling. So anything between 15 and 21 degrees C. Now, with this design, we can go up to 75 kilowatt per rack. So the previous design, we can go up to 50 kilowatt per rack. Here, we can go up to 75 kilowatt per rack. Again, the same challenges, dew point control, the fan control, also like how fast you want it to control or you want to run your fan, and what is the water valve or what is the opening of the valve that is controlling the coolant. Another important innovation is the chillers with free cooling. This is used more in in the second part of the presentation, which is the direct-to-chip or liquid cooling. However, I am seeing this now getting into air-cooled data center as well. And what you have here is you have a chiller that can operate either in just a chiller operation or chiller plus free cooling or completely free cooling operation. And that depends on what is the ambient condition. So if the ambient condition is low enough, then you do not need to run your compressor. And all you need to do to provide cooling for your water is to basically create having this runaround coil with this indirect heat exchanger to cool your chilled water loop. So this can provide cooling, especially for systems like what we will talk about later, because with the liquid cooled data centers, the chilled water temperature is much higher than air cooled data center. With free cooling, what we are doing here is we are actually running both the compressor, but also running this economizer. And by doing so, you can improve the overall performance of your chiller significantly. All right, so overall, the limitation of air cooling, as we said earlier, is what is the maximum capacity, 50 kilowatt, 75 kilowatt per rack with the active backdoor cooling. Air has low thermal capacity, so you need a lot of airflow. So your fans are big and noisy. When you are operating in high ambient temperatures, there are sustainability concerns. You cannot use waste heat, right? The heat that is wasted from the IT equipment cannot be utilized, and we need a new technology. So liquid cooling. The first thing is we are increasing the density with the server using GPUs, AI accelerators, and we can go up to 200 kilowatt per rack. And we need to achieve our sustainability goals. The first technology I want to talk about is what is called direct-to-chip cooling. And in direct-to-chip cooling, basically you have a rack, and inside this rack you provide the cooling water through the CDU. And the advantage is that it has better heat transfer, lower inlet temperature, less need for large fans. The cold plates use non-conductive fluids, and basically you can apply this and scale it in the current data centers, right? You do a retrofit to move your current capacity. So if you have a data center that is designed for 15 megawatt IT, if you retrofit your air-cooled rack equipment with direct-to-chip rack equipment, you can double your IT capacity from 15 to 30 megawatts. So just by doing this kind of retrofit, you can double your IT capacity. Of course, you need to make sure that you have the power from your infrastructure to power your equipment. So this is just a very interesting cartoon showing the way it looks like. And basically, you have your IT equipment inside the rack, and these are what we call the servers with the cold plate. And you have the coolant distribution unit, and you have your outdoor heat rejection equipment. So your coolant distribution unit will cool this coolant, right, using the outdoor or the chilling equipment, and send this coolant back into the rack. The PUE for a single phase direct to chip is around 1.13, and for two phases around 1.07. The key components are you have to have cold plate that are mounted on the chip, the coolant distribution unit or CDU, which includes a pump, a reservoir, loop, and a heat exchanger, and the secondary loop. So this is our secondary loop. So this part here is what we call the secondary loop, and this is what we call the CDU, which has inside the pump, the loop, and the reservoir. And then here we have our cold plates over the servers. The challenges is that there are some need to do leak risk management because the refrigerant or the coolant can leak. So we have to be careful about that. There is additional plumbing, and also the server design maintenance is additional, and coolant selection is important. You want to make sure it's dielectric, it's not gonna be conductive. You want to make sure the coolant is having good thermal conductivity and so on. So what is the temperature of the water of the water that we use? So we have here heat rejection equipment. So what is the water temperature? And according to ASHRAE, they created this guideline. So you can provide coolant like here, this water that is entering this blue line, right? Entering into your CDU can be at 17 degrees C, 27, 32, 40, 45, or greater than 45. Because we are actually extracting the heat with the cold plate directly. There is no air, so you can afford to use at higher temperature. So you can go even at higher than 45. So if you are providing at 17 degrees C, you use chiller. But now the chilled water temperature is 17 degrees C. So your chiller is operating at a much higher efficiency. You can also use cooling towers only because it's 32 to 40 degrees. Or you can even use a dry cooler. You don't need a cooling tower. You can just use a dry cooler. And then you can have supplementary cooling equipment to improve your efficiency. So if you are using a chiller, when the temperature outdoor is very cold, you can use a water side economizer. If you are using a cooling tower, if it's not sufficient, you might need to use chiller, or you might need to use district heating system and and use it as a preheating. So basically, this would be your waste heat recovery technology for district heating plants. Now, it's important to note that as we move from low temperature to high temperature, what that means is that we are going to consume more water. So if I'm sending water at 17 degrees C, this pipe is small. If I'm sending water at 45 degrees C, this pipe has to be large because I'm sending more water, right? Because the capacity of the CDU is the same. Let's say this rack is 100 kilowatt or 120 kilowatt, right? So this CDU has to process 120 kilowatt, and the 120 equal m dot Cp delta T. So the delta T is the water exit temperature minus the water inlet temperature, and the exit water temperature cannot be hotter than what the exit from the refrigerant or the cold plate can be. So there are some limitations. We have to be careful about that. Now, do we need a coolant distribution unit or not? That's a very important question. And the benefits of having a CDU is that it isolates the water quality problems. So if there is your chilled water plant or your cooling water plant has particulate by biological matters and so on and so forth, you don't have to worry about this getting into your cold plate. Also, you have a good thermal isolation. So your water volume that is cooling your IT equipment is more controlled. Your leaks are more controlled. Your maintenance is more controlled. Fluid properties are more controlled. Someone who can come and say, "Oh, I want to put this additive to improve thermal conductivity." If you do it on the small amount of water for your CDU, that's much easier than doing it on your plant. And then finally, there is this clear demarcation between the customer and the IT manufacturer responsibility. The main challenges is that with the CDU, you have to pay more, so there is an additional cost. It also makes the system more complicated, and there is an additional maintenance measure because you are adding this equipment with the pump, with the heat exchanger. Sometimes there might be some reliability issues of the additional components like the pump inside the CDU. And finally, there is a penalty in terms of energy efficiency because you are adding this heat exchanger, which result in an approach temperature inside between the coolant or the customer coolant, what the chilled water that I'm creating, and the cold plate. as well as the pump energy. This is a typical server design. And in this server, you can see this is the main board, this is the RAM, this is the CPU. And you can see here that I'm not getting all my cooling using the cold plate. But typically with direct-to-chip, 80% of the cooling is achieved, 80% of the cooling is achieved using the liquid, and 20% is achieved using air. So basically, up to 55 degrees C goes in, and what leaves is up to 60 degrees C. So if you remember from ASHRAE, we said 17, 27, 30, 35, and so on, up to 55. So the maximum is 55, and the maximum it leaves is 60. You cannot have it leave more than 60. This is very important. And just to give you a visual, this is what looks like an air-cooled data center, air-cooled rack versus a cold plate rack. So you can put too many, like here, you see how big this is. You see how slick this is. So it actually, you are packing more IT power in a much smaller footprint. Now, what are the benefits and challenges of direct-to-chip? You have higher thermal efficiency, which improve higher compute density. You have potential lower fan airflow. You also have better temperature uniformity, which means you have better reliability for your components. Also, with the waste heat, because now water is leaving at up to 60 degrees C, so 60 degrees C water can be used as a waste heat source. The challenge is you have to pay extra for your equipment. The architectural changes to the server and rack design. There is an issue with fluid management because you have to use dielectric fluid, and you want to make sure that there is proper leak detection, and also the integration with existing cooled infrastructure. And I've seen systems where we are slowly retrofitting D2C with or retrofitting all the air-cooled equipment with D2C in the same data center. So what we understand from this is that D2C is a strong stepping stone towards full immersion, but it will require hybrid integration approach. So it's not the best, but it is kind of a good stepping stone. All right. What is a new technology, a really good technology? So we like last time I was at the ASHRAE Expo in January. This was making spinning heads, right? Which is single phase liquid immersion cooling. All you do is you place your servers inside open liquid boxes like this, right? So you have a coolant here, and this coolant is cooled using a CDU, your coolant distribution unit, right? And this coolant distribution unit cools with the chilled water or water from your facility. Now, the design of this server box is interesting because you want to make sure there is no corrosion, there is no erosion, and so on. It contains the dielectric fluid, and the dielectric fluid can go in and out and absorb all the heat from the servers. Then there is the next technology, which is two-phase liquid immersion. So here we said it's enough to keep the liquid in single phase, so it does not evaporate, right? Now we said, what will happen if this liquid boil? Actually, if the liquid boils, then we will improve the performance. But if the liquid boils, we cannot keep it open. We need to keep it closed, right? So now we have what we say two-phase immersion cooling, again using dielectric fluid that boils. It has to be contained in a contained equipment like this, more expensive equipment, more expensive servers or racks. And what happens is, if you look here, you have your server, the heat would boil the dielectric fluid, and the boiled fluid go up, rise, and condense on this heat exchanger and drop back again, and the cycle continues. So there are two benefits. The first benefit is that you are using boiling heat transfer coefficient, which is much higher than natural convection heat transfer in single phase liquid immersion. The second thing is you are using the latent heat of condensation, so you can achieve much higher capacities. And I have seen up to, like, I have catalog data for more than 200 kilowatt per rack. So the figure, this one on top here is 100 kilowatt per rack, but I have at hand 250 kilowatt per rack. So the challenge is you have infrastructure for handling the vapor. How are you doing it? And you can see that this becomes very challenging. Also, the fluid selection is important. Possible component compatibility can be an issue. So you cannot just use any server. So you have to work with the server supplier to make sure that the server is compatible with your system. However, this is gaining traction in high-end DC or dead center cooling applications. All right, just to summarize what is the difference between single versus two-phase immersion. So if you look at single-phase immersion, you have a box here, and you have your servers inside the box, right? So what you do is you have your single phase, you have your single phase dielectric coolant. It goes into your CDU. It cools down using your heat exchanger, right? This is a pump here, and then it goes back into your server rack. So you have your CDU, and then you have your coolant, your plant cooling system, right? And your plant cooling system can be, as we said, chiller, cooling tower, or dry cooler. So you have this thing in the middle, which would result in additional additional delta T and additional pump power. With two-phase, it's much easier because all you have is you have your server here. This is a hermetic design. And what happens is you have your chilled water or cold water or cooling water goes into your condenser, leaves back. So all you need is a pump and a heat exchanger with your plant. And here, the refrigerant or the dielectric fluid that boils go up, condense on the heat exchanger, and goes back down. So it's a much simpler design. So while this server is expensive, the entire or the balance of system is going to be cheaper because you don't need all the additional components like the CDU. So if I if I want to compare between direct to chip and immersion, if you look at the coolant contact in the direct to chip, you need to have a cold plate on the chip surface. And when you add the cold plate, that means that you need to have an interface resistance, and that means that your coolant temperature would be at a higher needs to be at lower temperature to achieve the same chip cooling level. Whereas with immersion cooling, the entire server and the components are immersed in the fluid, so you can achieve the same cooling with much higher coolant temperature. The infrastructure change in D2C is moderate. You need to probably change the rack and add some piping. With immersion cooling, you actually have more radical change, and it's more of a greenfield design than a retrofit design. The heat removal capacity for D2C is high, but again, limited to how much the cold plate can handle, whereas for immersion is very high. So the highest D2C I have seen as a rack was around 120 kilowatt. The highest single phase immersion cooling server rack was around 150, and the highest two-phase was 250. This is, again, the numbers that I have. Again, I might be a little bit outdated, but this is the numbers that I have. The airflow requirement for D2C are reduced because I told you need 20% air-cooled, 80% liquid-cooled. Whereas for immersion, you don't need air at all. You just need a little bit of air just to make sure that people do not die inside the data center. So you need enough air to provide cooling for that data center air so that people are comfortable enough. In terms of maintenance and service complexity, the D2C is moderate, whereas immersion is more complex. And in terms of life cycle consideration, D2C has medium complication because it is a system in progress, whereas the immersion technologies have higher upfront cost, but potentially they would have significant savings over the lifetime because you don't have to pay much electricity. In terms of use cases, the D2C are for high density racks and upgrades and hybrids, whereas immersion, when you are doing high performance computing, AI, new builds, and ultra high density applications. So in terms of environmental benefits, we are like water and energy reduction is important. Immersion cooling significantly reduces water and energy consumption in hardware operation. There is lower carbon emissions and improved hardware lifespan. And these are again a reiteration on the implementation challenges. We are saying that liquid cooling infrastructure is important and it requires new servers and the retrofit cost can be high. Again, there are issues with compatibility. In terms of serviceability, immersion tanks may change access to equipment. Like it's not easy to swap out and maintain equipment. In terms of standards and metrics, the traditional PoE might not be sufficient. We need probably new metric or define PoE in a new way so that we can capture the impact of additional power used in immersion cooling system. While we are going to reduce the air cooling fan power, probably there is other heat rejection, which is the other end that we talked about, like here. Let me go back to this figure, which is this box here. What is the heat rejection here? How are we doing this heat rejection? So we said in this slide, heat rejection can be done using chillers, cooling towers, or cooling tower or dry coolers, right? So we are adding another layer of complexity to the system. And again, there are thermal and plumbing risks. And finally, there is a great opportunity for waste heat recovery. I'm running a little bit late, but there are hybrid systems. So what we call hot water loops for heat reuse. These are basically when you are in D2C leaving at 65, you get this hot water into a district heating plant, so you can preheat or provide heating to systems, so significant use. You can also use this for source energy for your absorption chillers, especially low temperature absorption chiller. Also, AI-based control and optimization is very important because there was a huge debate on how to optimize the performance of CDUs, and it was found out that you can create optimized sequencing using AI. And finally, in terms of microfluidic cooling, rather than using cold plate. So again, since we know that D2C is a stepping stone and would probably be a good option for retrofit, and there is significant bank of data centers. So instead of using completely destroying them and going to immersion, looking at ways to do the retrofit with D2C, rather than going to the cold plate, which has some limitation, going into the microfluidic cooling would unlock significant potential for improvement, because the microfluidic means that you are going to cool the chip directly, and by doing so, you are going to remove a layer of thermal resistance. In terms of future outlook, the microfluidic or the coolant channels inside the chip packaging, which is going to push the thermal management deeper. Two-phase cooling becomes more mainstream as the power density is going to continue to rise. Again, the waste heat reuse becomes standard, and sustainability metrics will evolve with time. So PUE and WUE are not going to remain the standard. Other features or other metrics will continue to evolve. And finally, geography and climate will drive design choices. So in hot climates, water scarcity, energy costs are going to push more towards liquid immersion. Unfortunately, I couldn't present today. I have a very interesting study that shows that in different climates, the choice between air-cooled, D2C, single-phase, two-phase can vary, and I'll present this in the next ASHRAE. So stay tuned. So if you come to ASHRAE, try to attend my lecture. So again, that center continues to grow, and one of the key lever arms for efficiency and sustainability is to improve efficiency, and also it helps us to improve the density of data center, and we can no longer rely on air cooling. Next generation technologies like direct to chip or single phase immersion and two-phase immersion are going to be kind of the mainstream. People are still apprehensive regarding two-phase immersion. However, I have worked on it. I've done a lot of research, and I believe it can significantly provide significant energy saving, and also life cycle cost saving. And for organizations planning data center growth, especially AI and high performance computing, the liquid immersion cooling is no longer optional. It is becoming a strategic necessity. With that, I'd like to thank you. If you have any questions, please let me know. I see like 34 questions. So for that, I'm not sure what is the best way of doing it.
Thank you so much. Thank you, Dr. Omar, for this prosperous presentation. And yes, we have questions in the Q&A. If you would allow me, before we answer the questions, I would like to thank you again with the introduction that I had for you, because I lost connection before, and I apologize again for this. We had Dr. Omar Abdelaziz. Dr. Omar is Associate Professor of the Thermofluids with over than 20 years of experience in R&D and project management, and he earned his PhD in the mechanical engineering from University of Maryland, College Park. He specializes in energy efficient building technologies, sustainable energy production, and alternative heating and cooling systems, including lower global warming refrigerants. He also served as a senior fellow at the U.S. Department of Energy's Building Technologies Office for 2 years, as he led the Building Equipment Research Group at ORNL, overseeing a diverse research program with an annual budget of millions of dollars. And also, he's an active member of several professional organizations, including ASHRAE, of course, and served as a co-chair of the Refrigeration, Air Conditioning, and Heat Pump Technical Options Committee, RTOC, for the United Nations Ozone Secretariat Techno-Economic Assessment Panel. As internationally recognized expert, he has published over than 100 peer-reviewed papers and holds several patents. Wow, this is the introduction you should have had at the first place. I'm sorry, because I know you introduced yourself quickly, but I took time to summarize this bio, so I have a great bio here, I had to tell. Thank you so much, Dr. Omar. And now we can have the questions. If you would like me to go through it, or would you like to read it?
I'll go through the questions. I'll read the questions and try to answer them as much as I can. So
Great.
there is a question on the psychrometric chart. So I will go back to the psychrometric chart. So this one, and the question on the psychrometric chart was how do we look at the dew point and wet bulb, dry bulb, relative humidity, and dew are aligned, and how to select the range of temperature and humidity set points. So basically, as you said, as you see, the black box or the black area here, this is what we call the recommended zone. So if you operate is within this recommended zone, you are fine, right? And then if you remember, there was an earlier slide, this one, you see A1 is the extended zone. A2 is the further extended zone. You can operate all the way to A4. But A4 is kind of okay for the different level, like it depends on the equipment that you are using. People usually only work in A1, not the recommend, like extend beyond the recommended and work in A1. So if we are in A1, you are going to probably be all the way to 82, right? Or 85. Let's call it 85, right? So it's gonna be like this. This is your zone. So let's say I want to have my conditions here. So if I want my conditions to be at 85 and 50%, right? And the outdoor conditions is here. So I will I will cool my equipment. I will cool my air. I will do wet bulb cooling. So I move along a constant wet bulb temperature. And then as a supply, what it will do inside the room is that it will have sensible heating. So it will have sensible heating all the way to 85. So that means that if I want to calculate the amount of airflow is going to be related to the difference between the point that I'm supplying and 85. So if I am here, let's say, which is the worst condition, right? So how does that compare? Like how much cooling can I provide if I'm here? The cooling, the lowest, the temperature, the wet bulb temperature that I can achieve is 77, right? So I only can achieve up to this point, right? So this point is what? Go down. This is 81. So at this condition, I will have to basically push a lot of air because I want to move from here back to 81. From 81 or from 81 to 83. So CP, m dot CP delta T equals the capacity of the data center. And by doing so, I would see that the volume flow rate I'll be pushing at this condition, which is 1 to 11 hours per year, is a lot. But if I look at the worst condition, that is 12 to 22 hours per year, which is this one, right? Then the worst case, I'm not pushing much air. So it has to be designed like, do I care about the worst case 1 to 11 hours or the 12 to 22 hours? Or do I look at the ASHRAE extreme case, which is 50 years extreme case, which is this one. And with this one, it looks like I can I can only get to 85. That means that I cannot not meet the A1 condition, but I will meet the A2 condition. There was another question about the humidity. So what I said, let me reiterate that very clearly. If your equipment is seeing 65% relative humidity or lower, 65% relative humidity or lower for 98% of the time or more, there is no issue whatsoever. So basically, if you are supplying at 80% and then you mix with the room, you will definitely be lower than 65 because you have to go like this. But here, you probably are going to go to 70%. So sometimes there are some maybe 1 hour per year, 2 hours per year, where there are issues where direct evaporative cooling can be a problem. So the issues of 20 years extreme conditions are enough. That's why I said no, I use the 50-year extreme, I don't use the 20-year extreme. So in my designs, I use the, where is that? So there is 10 years extreme, 20 years extreme, and 50 years extreme. So I use the 50 years extreme, not the 20 years extreme. The difference between the free cooling and the pumped refrigerant economizer, the difference is that in free cooling, here, you are actually using the same refrigerant line, right? So you are not having an additional heat exchanger. So your condenser, basically you are disabling your compressor and having your subcooled refrigerant pushed through your system and then back into your condenser. So by doing so, you have a design in which you are having a the same heat exchanger the same piping. You are not separating this pipe, the pipe of the what is it called? The pump of the pump from the pipe from the or the from the condenser to the evaporator. So it's kind of in line or integrated economizer. Whereas if you look here, right? With the free cooling, we are adding a new heat exchanger and a new coolant, typically uh, propylene glycol. So it's not refrigerant because this is a pump and this is a coolant, and you have another heat exchanger. So it's a little bit different. Two-phase direct-to-chip cooling. So in two-phase direct-to-chip, the difference between single-phase and two-phase is that you see probably it will appear in this slide, right? So in single phase, I have a liquid coming in at 55 and leaving at 60. Whereas in two phase, I would have a liquid coming in at 55, but leaving as refrigerant or as a vapor at 55. So this fluid goes in and boils. And by doing so, I'm going to create or use the latent heat of vaporization of the fluid. And by doing so, there are two improvements. The first one is you are using boiling heat transfer coefficient, which is higher than the convection heat transfer coefficient. The second thing is you use smaller pipes because you need less refrigerant flow. So the problem is the dielectric fluids that boil are more expensive than the dielectric fluids that are single phase. The dielectric fluids that boil are also more difficult to work with because they are volatile, and we have to be careful about how to work with them. All right. Now I see a question that I'm not understanding. Why GB200 servers cannot be used in immersion cooling? That I am not sure I understand. What is GB200? Can you elaborate, Mr. Muhammad Bilal? All right, Mr. Tawfiq. So basically, for direct to chip cooling, it's actually fairly simple because these are swappable, and the cooling component here, these are quick plugs. So you have valves, you close the valve, you have quick plug, so you can easily quick plug or what we call it quick connects. So you quick connect, disconnect the inlet and the outlet, and you can take the whole server out, maintain it, put it in, swap it if you want. That's easy. For immersion, if you look at this figure, for single phase immersion, it's easy because this whole thing does not boil. So you see the handles here. So you can, and these are safe fluids. So you can put your hand on these handles, pick your entire server up. Of course, you have to unplug all the electricity and all these things. This is dielectric fluid, so you will not get shocked or anything. So it's safe. I think the main challenge is with this one. So with the two phase, the problem is it's boiling, right? So since it's boiling, you cannot have, it's not hot swappable. So you will have to kind of shut down the operation in order to be able to swap the server. Again, for the two-phase, there is a way to contain the fluid because you actually have to go into service mode, and when you go to the service mode, so the selection of the dielectric fluid is such that it is liquid at room temperature. It's not vapor at room temperature. It's liquid at room temperature. So since it's liquid at room temperature, there are little fumes or no fumes, and of course, the operators have to wear proper PPE. A question on, do you think modern cooling techniques such as magnetocaloric or elastocaloric systems could be good candidates for cooling data servers? Um, I I worked on I'm actually working on a magnetocaloric project and have worked on elastocaloric before in the past. I I like that you enjoy it, Mr. Abdul Muez, but I don't think it's possible that we can use these technologies in data center. There is a question about compressor put in crack unit. So this question again pertains to the design choice of the manufacturer. Some prefer the compressor to be placed in the same unit with the inside the crack just to make it more reliable. Some prefer to put it in outdoors. It's again a design choice. Do we get user requirements URS for that? I'm not sure I understand the question, Mr. Muhammad Mansour. What is URS? What user requirement URS for rack manufacturer? I'm not sure I understand the question. Mr. Muhammad Mansour Ibrahim, I'm not sure I understand your question. Do we normally get a user requirement URS for rack manufacturers with recommendation for cooling system required? So I'm not sure I understand your question. But typically, user requirements are for the like the rack the system architecture, and then as a consultant, you will have to give them potential providers. I'm not sure if they have a pre-qualified list or not. So with regard to data centers, the criteria for indoor air quality is mainly as I showed in this chart, in this psychometric chart. Right. So again, these are the allowable envelopes, right? And these are based on levels of pollutants verified by coupon measurements as indicated in this section. So again, there is section 9.4, section 2.2 and standard 9.4 that would define that. Unfortunately, I don't have that on the top of my list, but if you follow up with me via my email, I'll be more than happy to find that for you. When it comes to the design consideration with ASHRAE 20 years maximum temperature, I think it makes more sense to use the maximum dB plus the average bulb for the location instead of the maximum wet bulb, isn't it? Because the same two maximum temperature would coincide together rarely. So, Mr. Yasser, I agree with you, but when we design for direct evaporative cooling, you design for the maximum wet bulb. When you design for dry coolers, you design with the maximum dry bulb. I'm not saying use them together. It's just that you use the maximum dry bulb when you design for dry coolers. Use the maximum wet bulb when you design um, for the direct evaporative cooler. And if you want the point on the psychrometric chart, the best way to do it is to actually use projected data from IEA. The immersion technology actually does not affect the data center redundancy requirements. The redundancy requirement is based on how you design the architecture of your data center. So the redundancy requirement depends on how many racks that do um, the same uh, the same thing are there in the data center, and are they on different uh, electricity supply lines and so on. So the new immersion technology does not affect that. What affects it is the system architecture. Unfortunately, I'm not going to provide a PDF of this webinar, but I'm going to allow ASHRAE to share the video. What is the desired temperature and humidity for high ambient markets so for high ambient markets and like UAE and Kuwait, my recommendation is to again operate or design somewhere at 27 and let's say 50%, but I would go all the way to maybe this condition, which is going to be 32 and 40% RH as our design criteria. We can actually go up like this and go to 50% without any problem. The new AI data center have different behavior in matter of load fluctuation than typical one. Can you highlight this issue? Thanks, Mr. Muhammad. Actually, this is a very important question because uh, that's what actually I tried to discuss, but I was kind of rushed towards the end. Where is that? So AI, actually, the AI data center can be idle, and then all of a sudden they get a question that they have to run all their models, and that can basically go high load, low load, high load, high load, low load, and so on. And by doing so, the IT equipment would actually the cooling load would fluctuate significantly. Air cooling cannot easily manage that. However, if you go to direct to chip, you can kind of track that with a proper AI-based control optimization. So if you have an AI-based control optimization that can have the pump of your CDU operate with variable speed control so that it can change the flow rate of your coolant of your CDU coolant, the coolant inside the CDU to basically track this cycle of the data center. That would be great. Now, with single phase and two phase immersion, this is not going to be an issue, right? And that is why people love immersion technology, because especially two phase immersion. Because with two phase immersion, what will happen is two phase bath, the bath of the immersion coolant itself is creating kind of a storage facility, is like a storage, right? So if you have a burst of IT processing power, or what happens is some of the coolant will bubble, right? And it would take longer for the coolant to condense that, right? But eventually it will condense. So, and at times where there is no load, you are condensing more of the vapor on top of the bath, and eventually things will balance out through time. So that's why two-phase immersion is very attractive for AI applications. Are there available temperature ranges specific in the ASHRAE guidelines intended for the cold aisle supply conditions? Yes, actually, if you open ASHRAE 90.4, which is available online in the ASHRAE Standards online database, you will be able to find all these information. It's available, it's free, because it's part of the ASHRAE and U.S. Department of Energy commitment for building energy code savings. Mr. Abdulrahman Mahmoud, Again, the question about data center air quality and the concern with evaporative cooling, based on the experience in the US, it's not a concern because people do not stay long time inside the data center. Data center is for machines, it's not for human, and the air quality is not an issue. As you can see in the anatomy of the data center that I have shown earlier, right? People do not stay too long in the data center, right? The point of presence is here, right? This is the point of presence. This is the data hall. So if these air handling units are back evaporative cooler, you take outdoor air, you humidify it and push it in, right? And you have somewhere of exhausting the humid, hot, humid air. That's not going to create an issue for air quality. What is the refrigerant module we use? The refrigerant module we use is, I don't know. I don't know. I don't understand exactly what you are asking, Laith, but there are different refrigerants that are used in the chillers. Like in this chiller yard, for example, we can use anything like uh, the same refrigerants used in typical building design. However, now with the push towards sustainability, they prefer to use lower GWP refrigerants. Why do we use pump after uh, compressor in case number one? I don't understand which one. Case number one. This one? The pump is not operating. This is the gray means that there is not working. Green means working. So in mode one, the pump is not running. It's actually just like here, everything is gray means that it's not working. So it's just this is the coolant. It goes into the first heat exchanger, but it's not working, and then to the second heat exchanger. Of course, clever people put a three-way valve to avoid the pressure drop in this heat exchanger when they don't need it to operate. Uh, I cannot present the main steps for design cooling the center. It's actually a whole a workshop, and design day probably can take half a day or more. Unfortunately, Mr. Lath, I will not be able to do it today. In terms of sustainability requirement, there is actually a very good and informative uh, um, procurement guide by by UNDP, that was developed to say how do you procure equipment and data for data center, what should be the PUE, what should be the water use effectiveness, how do you select equipment, how do you look at CUE, and so on and so forth. If you are interested, I'll be happy to share that document with you. You just have my email, and I'll be happy to do it. Okay, A1, A2, and A3. Mr. Sawi is asking about these. So these envelope actually indicate the temperatures, this what we call the supply IT temperature, the temperature at the supply IT equipment. So it's the mixture between the supply air temperature and the return air temperature. Some people can think of it as, almost supply air temperature, but in the in most hot air, hot, cold air, hot air, hot air, cold air, hot air aisle, we think of this as the cold air aisle temperature. Mr. Muhammad Arafa is saying they remove the compressor itself from the cycle, but now there is a wise to add a pump. Please explain. So if you remove the compressor from the cycle, that means that you need to still have a way to run your refrigerant. So in Frankfurt, which is a cold weather, right? If you are operating your system at higher temperature, you don't need to create a direct expansion, and you can basically, in a city like Frankfurt, your temperature is year-long below 35 degrees C, so you can actually have a pumped refrigerant loop. So what you do is you pump your refrigerant between the condenser and the evaporator, and you get rid of your compressor completely. Laith is asking whether we can use ammonia. There was actually a case study done by one of the UN implementing agencies to use ammonia as the refrigerant in a chiller for a data center, and it's possible. The problem is this is a very difficult refrigerant to work with. Of course, data centers are nice because you have a chiller yard of, 10,000 ton or something like this. So especially for hyperscale data center, so it's a big data center or a big chiller. So you can afford to have your maintenance engineers for an ammonia plant. However, it's not necessarily the best, the most used refrigerant. I understand Mr. Mustafa Abu Al-Basyuni about the indoor air quality and the IT equipment corrosion, which is accelerated. And that's again my answer. So that here, yes, the acceleration, there is a equipment corrosion acceleration if you are going to operate with a temperature with a relative humidity higher than 60%. So if your return relative humidity is higher than 60%, you will corrode your equipment, but you will not operate at higher than 60%. That's what I said, is that you want to operate at I'm struggling to get my let me see if I can have that. Is there a way to I use a highlighter? 1 second. Maybe I can actually do it this way. So let's say I want my conditions. This is my line, right? This is my operating line, right? And I'm okay to achieve. This is my line, and I want to be 60%. So I said actually 65, right? I said 65. So 65 is this line. So that means that this is the maximum temperature I can have as my return, right? So this is my return maximum. Okay. All right. So if I am working with the worst condition, this is the worst condition in Phoenix. I work with direct evaporative cooler. So what I do is I do evaporative cooler, right? I say I can only hit 80%. Above 80% is not good. So I hit 80%, right? With 80%, I have between this one and I go in the room, I go sensible heating only. So I'm not gonna go here, I'm gonna go here, which is even lower relative humidity. So I'm not going to leave the room with RH of 65. I'm going to leave the room with an RH of, let's say, 62. Does that make sense now? Again, let me try to do it. So this is the maximum design temperature. Okay? And we said, I don't want to be above 65. So this is 65. Where is 65? Here. Right? So this is my maximum condition. Okay. So if I go and say, I want to see what is the worst case condition. So the worst case condition is this one. I humidify this one to 80%. All right. So I can achieve this point. If this is my supply air temperature, right? This supply air, if it goes into the space, it will go sensible only, right? So my return air would be this return air. So this return air would have a relative humidity less than 65%. And to know them, the flow rate is going to be basically this is delta H, H room air. This is H supply air. Or if I know the TP, delta T, whatever you want to do it with it. Not on this page, Doctor. Okay, most Google DC is green, yes, and that is why, because they are using what we call free cooling or direct evaporative cooling, or um, uh, cooling from underground facilities. So they use nature to provide the cooling. So geothermal cooling, they use river cooling, they use just free cooling from the air. They put them in cold places to use free cooling from the air, or they use direct evaporative cooling. All right, any questions? All right, thank you.
Thank you, Dr. Omar, so much. Thank you for your time, and thank you for being with us with Pyramids Chapter. Thanks everyone for joining us for today's webinar, and please follow us for more events. Thank you so much.
Thank you.
Bye. Have a great night.